Assalamu alaikum everyone and welcome to the channel. I am Sara Javed and today I am super excited to take you through a Kaggle competition I recently joined, the Flight Rank 2025 Aero Club Challenge. Imagine you have thousands of flight options for a single search. Asking one highly complex model to carefully compare every single option is computationally very expensive and slow. The two-stage approach is a clear solution to this problem. So, what this competition are about? Well, in simple words, the goal is to build a smart model that can predict which flight a business traveler is most likely to book from a list of search results. Now, you might be thinking, why is this even important? Because business traveler is not as simple as booking a vacation. For business travelers, price is not always the top priority. They have to deal with company travel policies, tight meeting schedules, and of course, their own convenience. That's where a good recommendation system comes in. It helps cut through the clutter, shows the most relevant flight first, and make the whole booking process faster and way less stressful. And for travel platforms, that means happier user and better booking rates. Now here the real challenge. This is a group wise ranking problem. That means every time a user searches they are shown a group of flight options and our model needs to rank those flights. Not just say whether they are good or bad, but actually sort them from most to least likely to be chosen. And how do we know if our model is doing well? The competition uses something called hit rate at 3 as the evaluation metric. Basically, it checks whether the flight the user actually picked is in the top 3 predictions our model gave. A perfect score of 1 means we nailed it every single time. So that's the challenge. Alright, now let's talk about the data. The organizers provided a massive dataset to work with. The two main files are train parquet and test parquet. Along with that, there was also an optional and honestly enormous 50 GB archive of raw JSON files, which was perfect for anyone interested in doing deep level feature engineering. Now let's break it down. The main training data contain millions of rows, where each row represents a single flight option from a user search session and it's packed with rich information. We are talking about user details, flight route and timing, pricing, future flight metadata, company travel policies, and much more. But here the tricky part, the dataset is so huge you cannot just load it into memory on a regular machine. If you try, your notebook will crash before you even get started. That's why for my project I had to make sure to start the session in a high memory environment like a Kaggle TPU or highly RAM runtime. That gave me the breathing room to explore and process the data without anything breaking down. Alright, with that strategy in mind, let's jump into the code and see how it's implemented. We start by setting up our environment. The percentage capture command at the top just hides the long installation output to keep the notebook clean. We are installing server key libraries, XGBoost and LightGPM for our models, Polars as a super fast way to handle our data, and Aptuna for a hyperparameter tuning. Next, we import these libraries into our session. The most important one here is import Polars SPL. Polar is a modern, incredibly fast data frame library that's great alternative to Pandas, especially for large dataset like this one. We also import our modeling libraries and set a random underscore state to ensure our results are reproducible. Here we load our data using pl.read underscore parquet. We load both the train and test set. A key step here is pl.concat train and test. We immediately combine them into a single large data frame. This is a powerful technique because it allows us to apply all our feature engineering steps to both the training and test data at the same time, which guarantees consistency and prevents errors. This next block is the heart of our data preparation. We are using Polar expressive and effective API to create a whole suite of now new feature from the raw data. Let's break down what's happening. We start with a helper function to convert duration string like 1 day 10:30 into a single number representing the total minutes. This makes it usable for the model. We create new feature like text underscore rate, a long underscore price to handle the wide range of prices, and n is underscore one underscore y flag to identify the trip type. This is critical for a ranking problem. We use rank over rank underscore id to calculate the rank of each flight price and duration within its own search group. This tells the model if a flight is the first cheapest, fifth cheapest for that specific search. We create powerful binary flag like is it underscore cheapest and is it underscore min underscore segment. We also do something clever by finding the price of the cheapest direct flight in each group and the creating a feature called is underscore direct underscore cheapest. This is a very strong signal for business travelers. We extract the hour and weekday from departure and arrival times to capture patterns related to time of day and week. This block takes our feature engineering to the next level. Here we first calculate group level statistics like the minimum, maximum and average price of each search and then join them back to our main data frame. This allows us to create powerful interaction feature like price underscore vs underscore min. How much more expensive is this flight compared to the absolute cheapest option the user was shown? Is underscore mode is underscore carrier. Is this flight operated by the most common airline in the search results? These features give the model deep conceptual awareness of the choices presented to the user. Now we define our final list of features. We create a list of cat underscore feature that our model can handle. Especially, we also create an exclude underscore calls list to remove identifiers, target variable, and columns with too many missing values. This helps to reduce noise and focus the model on the most informative signals. Here we prepared the data for our two-stage pipeline. First, we encode the categorical feature into numbers so all our model can use them. Then we split our data into training, validation, and test sets. This is doing using a simple time-based split based on row counts, which is a robust way to validate models on this kind of data. It's time for stage 1. We create light GBM dataset objects which are optimized for performance. We then define a relatively simple and fast set of parameters for our light GBM model. The goal here is speed, not perfection. We train the model using lightgb.train and we use early underscore stopping to automatically stop training when the performance on our validation set stops improving. This is the bridge between our two stages. I have defined a filter underscore top underscore k function. This function takes the stage 1 model we just trained and uses it to predict scores for all the data. Then for each search group, it to select the top 15 highest scoring candidates. We apply the function to both our training and validation sets, creating new, much smaller data set for our next model. Welcome to stage 2. We now take our smaller filtered dataset and prepare them XGBoost using its dmetric object. We define a new set of parameters for our XGBoost model. These can be more complex because the model is only training on the top candidates. We then train our final re-ranking model again with early stopping, but this time we can be more patient because the dataset is smaller and of higher quality. After training, we need to see how well our entire pipeline performance. We use our state 2 XGBoost model to make predictions on the re-ranked validation set and calculate the hit rate at 3. This gives us a reliable estimate of our final competition score. Finally, the submission process perfect minors our two-stage pipeline. First, we use our first stage light GPM model to predict on the entire test set and select the top 15 candidates for each search. Then we use our powerful stage 2 XGBoost model to predict only on these top candidates. We generate task rank based on these final more accurate scores. A curical final step is to merge these rank back with the full test set, giving a low priority rank to any flight that did not make it into our top 15. This ensures we rank every single flight as required by the competition rules. We then write this to our submission.csv file. And that's how you build a two-stage ranking model from scratch. It's more advanced technique, but it's incredibly effective for problems like this with a huge number of options. We use a fast model to generate and candidates and a powerful model to find the needle in the haystack. If you found this deep dive helpful and want to see more advanced data science projects, please give the video a like and make sure to subscribe. Thanks for watching and I will see you in the next one.